Hi, AP Chem. Welcome to the last application of equilibrium. We're going to talk about equilibrium in terms of dissolving salts and also the opposite reaction of those ions coming together and precipitating a salt out of a solution. Okay, so here's the deal. This can be the toughest application of equilibrium, or it can be the simplest. And it all seems to come down to the vocabulary, understanding the vocabulary. So that's where we're going to start in this chapter. We're going to start by talking through some of this vocab, because if you understand what the question is asking, precipitation and dissolving are actually really simple applications of equilibrium. It's kind of more of the same. So let's take a look at a couple words that you really need to know before moving forward. Okay, the first one is going to be solubility. So this is a common thing to ask, like, what's the solubility of sodium chloride in water at 25 degrees Celsius? What's the solubility of sugar? What's the solubility of calcium fluoride? And when they ask you what the solubility is, what they're looking for is an amount. Now, technically, it's going to be a concentration. It's always going to be amount per volume. But really what they're looking for is an actual amount. Now, it's the amount that dissolves to form a saturated solution. So let's just revisit what a saturated solution is again. Remember that when you put salt into a solution, if it is soluble, the salt is going to break up into ions, and you're going to have free floating ions until the solvent can't hold anymore. So usually the solvent is water. We're talking about aqueous solutions here, right? So when the water can't support any more ions, what happens is these compounds will fall to the bottom and form a little pile. And that's how you know that it's saturated, because you see solid present. If you don't see solid present, it's probably not saturated yet. If you add a little bit more in and it falls to the bottom, then it's saturated. The water can't support any more ions. So the question when we're talking about solubility is, how much do we add? For example, sodium chloride, table salt. The solubility of table salt is 357 milligrams per milliliter. So there's your amount. We can, for every 1 milliliter that we have, that's not a whole lot of water. For every 1 milliliter that we have, we can add 357 milligrams of salt, and it will dissolve in that 1 milliliter of water. If we add 1 more milligram, it's going to fall to the bottom because our water will be saturated. So solubility is an amount. In this case, we have communicated that amount in milligrams per milliliter. In chemistry, we deal more with moles than grams. So we deal more with the counted amount versus the measured amount of mass, right? So we'll see it a lot of times in moles per liter or per milliliter, something like that. But solubility is going to be that quantity. Now, the trick is when you're looking at an ice chart, where does that quantity appear? And what that quantity is in an ice chart, it's the equilibrium position of the actual salt. So if our reaction is calcium fluoride splits into a calcium and 2 fluorides, right? It's that solubility is not the initial amount. It's not necessarily the change. It's the equilibrium position of the salt. So this gets a little bit complicated. If we look at like this example of calcium fluoride, for example, CaF2 goes to Ca2 plus and 2F minus. Okay, let's look up the solubility of calcium fluoride. All right, and Google says it's 1.61 milligrams per 100 milliliters of water. Okay, so where would this go on our ICE chart? So what that means is if we put solid calcium fluoride into water, and it'll dissociate until it hits the dynamic equilibrium, right? At that dynamic equilibrium, we will have 1.61 milligrams per 100 milliliters of calcium fluoride, right? If that we have lost that much from our initial amount. We have dissolved that much from our initial amount, right? So that's our equilibrium position for calcium fluoride. And actually, we can fill that in for our change too. We have lost 1.61 milligrams per 100 milliliters of calcium fluoride. That's what this solubility means. And if you know that, then the rest of the ICE chart really falls into place, right? We know that if we lose one calcium fluoride, so we start with a calcium fluoride molecule. Remember, it doesn't actually exist as a discrete molecule. It exists as a lattice. So what we're talking about when it dissolves is that one unit with a ratio of 2 calciums or 2 fluorides to 1 calcium, one unit has broken off of the lattice and dissolved. Okay. So when that one unit dissolves, we get 1 calcium. So if we lose 1.61 of calcium fluoride, we're going to gain 1.61 calcium. And we get 2 fluorines, right? So we're actually going to gain double that amount, 1.61 in fluorines. Now, we have this amount in milligrams, which is hard for us to deal with in an ICE chart. So here I'm pretending that this exists in moles, so we can do this ICE chart in relative numbers instead of mass. If you were actually going to do this in mass, it'd get a whole lot more calculate-y, right? Oh, more complicated. You have to calculate a lot more. So let's just pretend it's in terms of moles. If I lose 1 calcium fluoride, I'm going to gain a calcium ion, right? It's going to break up into a calcium ion and 2 fluoride ions. 2 fluoride ions, because that's on my unit. So I'm not gaining mass here, but I am gaining number of molecules because my one thing has broken up into 3 things. So does my mass change? No. Do my units, my number of particles change? Yeah, it does. And so if I'm doing my ICE chart in terms of numbers of particles or moles, then this is what it would look like. So notice, again, let's return to this idea of what is solubility. When I communicate a solubility to you, it's going to be the amount of calcium fluoride, amount of your salt that you dissolve. What's my solubility? It's the quantity that dissolves in order to saturate a solution, which means it ends up as the equilibrium position of your salt. Okay, is it the equilibrium position of your 2 ions? No, because that's dependent on what you're talking about. What are those ratios? In this case, it's a 1-to-2 ratio, and so I would have to multiply that amount that dissolves to get the correct number of ions. Okay, so like I said, this little piece of vocab makes a world of difference. If you can wrap your brain around what solubility is and where it appears in the ICE chart, the whole problem falls into place. If you're confused about what solubility is and where it shows up in the ICE chart, this is going to be a very confusing problem for you. It's going to vary depending on what's present. What's the salt? Is there a common ion? Is it in water? Are there acids and bases present, right? All of those things can affect this, but it must satisfy your K. Remember, we're still talking about an equilibrium here, so it must satisfy your K. Speaking of K, that's our second vocab term. solubility product or solubility product constant is our K for this equation. Let me delete what I have so we can focus on that. Okay, solubility product or solubility product constant is the K when you're talking about a salt dissolving. Now, remember, K is going to match with a very specific equation. So KSP, or your solubility product constant, is going to match with this specific equation. It's going to be your salt dissolving, your salt as on your reactant side, and then ions on your product side. That's the reaction, not the reverse. You can't write ions as your reactants going to products as the solid, because that will be the inverse of KSP. So you got to get the reaction correct. As long as you get the reaction correct, it's just a very typical K. Now, it's a little confusing because at this point in time, we seem to have a million terms for K, right? It's called the law of mass action. That covers all of them generally. When we're talking about just an equilibrium reaction, we refer to it as the equilibrium constant. If we're talking about acids, we call it the acid dissociation constant. If we're talking about salts, we call it the solubility product or the solubility product constant. So it gets a little bit confusing because we have a million names for the same thing, right? But as long as you can understand the name, you remember the name, it's a very typical K, no surprises. You do have to remember, though, that solids and liquids do not affect your K. Remember, their concentration is essentially 1, right? And so their concentration doesn't affect the K equation. If we were to write the KSP for this equation we have up here, your KSP is going to equal the concentration of your products. So that's calcium raised to its coefficient. That's fluorine for the fluoride ion raised to its coefficient of 2 over 1, right? Because this is a solid, so it's not going to affect your KSP. So this is our KSP equation. You have to remember solids and liquids don't affect the KSP equation. You don't include them. And you have to remember that we raise it to the coefficient. Now, we didn't do this very often with acids and bases because acids tend to protonate one at a time, and we get a lot of 1 to 1 to 1 to 1 ratios. Salts aren't like that. Salts just dissolve the whole thing at the same time. So you're going to have coefficients. In this case, you're going to have to deal with coefficients. Okay, so KSP is just the equilibrium constant for this very specific reaction. It's going to have one value. If you want to know what the KSP for calcium fluoride is, you can go on Google and look it up. NaCl, go on Google, you can look it up, right? Just remember, if you change the temperature, just like any equilibrium constant, if you change the temperature, it's going to change as well. Okay, so now that we have all of this kind of worked out, let's put it to work here. In this case, we have copper 1 bromide. It has a measured solubility of 2 times 10 to the negative 4th moles per liter at 25 degrees Celsius, and they want us to calculate the solubility product. Okay, so just like all equilibrium things, we're going to write out the reaction, the ice chart, and the K, because that's what we're looking for, right? So our reaction has to be the solid going to ions, copper 1 bromide going to copper 1 and bromide. Now, they tell us we have a measured solubility of 2 times 10 to the negative 4th moles per liter. Okay, so remember, when they tell us you have the solubility, that's how much of your salt will dissolve. So we're going to lose 2.0 times 10 to the negative 4th moles per liter of our solid, which means we're going to gain 2.0 times 10 to the negative fourth of this, and 2.0 times 10 to the negative fourth of this. So does that make sense? If I have a copper bromide molecule, let's say I have 2 of them, copper bromide. If they dissolve, I'm going to get copper ions and bromide ions. So if I dissolve 2 copper bromide ions, I'm going to get 2 coppers and 2 bromides. Yeah, that makes sense. If I dissolve 2.0 times 10 to the negative fourth moles per liter of copper bromide, I'm going to get 2.0 times 10 to the negative fourth of copper plus and 2 times 10 to the negative fourth moles per liter of Br minus. Okay, so at equilibrium, this is what I have. Now I want to calculate the solubility product. So I'm going to plug it into my K equation. All right, so what's my K equation going to be? I just have one of each, 1 and 1, and I can just plug it in. 2.0 times 10 to the negative fourth, 2.0 times 10 to the negative fourth. Let's calculate an answer. And I'm going to get 4 times 10 to the negative eighth as my KSP. Okay, so like I said, super straightforward equilibrium problem as long as you can pull out these definitions. What is solubility? What does that mean on the ice chart? What is solubility product constant? If you know these terms, then the problem's very straightforward. If you're confused about these terms, it's a very complicated problem. All right, so when we get back together, we'll do a couple practice problems with that. Let's talk about relative solubility. So if they give you a Ka of acids, you can compare the strength of the acids, right? Well, if they give you the KSP, you can compare solubility of ions sometimes. So let's look at that a little bit closely. If you have the same number of ions that break up, then you can compare solubility of these, because remember the KSP is made up of the ions, the products, the ions multiplied together and raised to their coefficients. And so if we look at the KSP for these 3 salts, for example, they all break up into 2 ions. Every single one of them breaks up into 2 ions. So the KSP is going to be really similar for all of them. If we talk about solubility, we solve for solubility. It's basically the square root of the KSP, right? But if we compare it with salts that have different number of ions, like these 3 salts below, then our solubility is not communicated in a straightforward way from the K, right? Solubility is the X. KSP is the product of all the X's, right? So if you take all those X's from salts that have different ions, right? This one's going to be X times X. This one's going to be X times X squared. This one's going to be X squared times X cubed. I guess the square would be on the other X, right? So these products, solubility products, are really going to communicate different things. They're not going to communicate solubility in a very straightforward way. You have to actually calculate the solubility before you could compare how soluble all of these actually are. So when you're talking about how soluble something is or communicating that solubility, you really need to compare the X's, not the KSPs. I mean, you can calculate KSPs as long as all your salts have the same number of ions, but you can't do that if they all have different number of ions. You would have to calculate the solubility before you can compare the solubility, right? Again, it makes sense when we understand what solubility is and what that's communicating. So that vocab really is super integral to understanding this concept. Okay, there's also the same things that will affect acid and base dissociation will affect a solid dissociation or a salt dissociation, which is what we're dealing with when we're dealing with solubility, right? So the same factors will affect both of these. Common ions are going to affect both equilibria. Acids and bases will affect both equilibria. So let's look at the common ion effect in this case. What's the solubility of AgCrO4, so silver chromate, in a 0.1 molar solution of AgNO3? Okay, so we're going to put Ag2CrO4 into a solution of AgNO3. So what's in that solution? Well, Ag is going to be in that solution, and NO3 is going to be in that solution, floating around with some water ions, right? Okay, so we have this solid going into water and a bunch of ions. So just like acid-base equilibria, we have to consider what's present before we can move forward. Okay, so let's write out this reaction. Ag2CrO4 dissolves into 2 Ags and CrO4 minus. Okay, so we're going to have a 0.1 molar solution of AgNO3. So if we have 0.1 molar AgNO3, that means AgNO3, 0.1 moles of it have broken up into Ag and NO. So I'm going to have 0.1 moles of both of those. Now, NO3 doesn't affect anything, so I'm going to put a 0.1 for the silver. I don't have to include NO3. It's not going to react with anything. It's not going to be part of a dissociation. It's not going to affect anything. I'm just going to ignore it. Okay, so now I want to know what the solubility of AgCrO4 is. So again, I'm looking for solubility. I'm looking for that X. What is that X going to be? Now, I don't know how much of Ag2CrO4 is going to dissolve because that's what I'm looking for. So I'm going to keep that as an X plus 2X plus X. So my equilibrium positions will be X, 0.1 plus 2X, and X. So I can plug that into my K equation. So 0.1 plus 2X. Remember, you got to square that because of the coefficient, times X. And now we solve for X. Notice I'm going to get a very complicated equation here, but again, my KSP is really small, so my X is going to be really small. So anytime I add or subtract that X to a number, I can assume it's going to be so small it won't affect the significant figures of that number. So I'm going to make that assumption here, 0.1 squared times X, and it just simplifies my equation a lot. Okay, now let's do the calculation. Okay, yes. X is going to come out to be very, very small. All right, so X is going to be equal to, I have 9.0 times 10 to the negative 10. Very small. Okay, so there's my solubility of silver chromate in this silver nitrate solution. How does that compare to the solubility of silver chromate in pure water, which is here? It's smaller, right? So again, we see this common ion has suppressed the dissolving, just like it does in acid and base solutions, and just like we would expect it to according to Le Chatelier's principle. Okay, so we will do some of that practice together. Ions of acids and bases can act in the same way. So when we look at dissolving a salt in an acidic or basic solution, those ions of a base which is hydroxide, or ions of an acid, which is the hydrogen ion or the hydronium ion, they're going to act in the same way. Now, you don't have to do these calculations, but you do have to predict if it would be more or less soluble based on Le Chatelier's principle. So, for example, if we have magnesium hydroxide dissolving, right? Notice that the ion here is a base. So if we put this in basic solution, I would have an initial concentration of my base present. Would that tend to encourage magnesium hydroxide to dissolve or discourage it? According to Le Chatelier's principle, it would discourage it, right? So anytime we have a stressor, it's going to resist this. The equilibrium will shift to minimize that stressor, right? So if I already have a hydroxide present, it's going to dissolve less of my salt so that I minimize the hydroxide stressor. Now we could flip this. What if I add an acid in here? That acid's going to react with this to form water and actually remove it from solution. In that case, my stressor is that hydroxide's disappearing. My system's going to shift to replace it, and more of my salt will dissolve. And so ions from acids and bases are going to act just like common ions. And you should be able to predict which way the equilibrium is going to go based on Le Chatelier's principle. Okay. All right. So we'll come back together. We'll do some practice with that. And then we're going to get into precipitation conditions next time. So we're going to flip the equation. Instead of dissolving our salt, we're going to form our salt. Okay. Let me know what questions you have. I'll see you in class.